So the Holder's inequality is a generalization of the Cauchy-Schwarz inequality. It states that whenever we have two sequences, some a sub case and b sub case, I've got those right there, such that those a sub case and those b sub case are positive real numbers, we have that. When you just go on and sum up all of the terms in each sequence, and then you raise those sums to the power of q and some p respectively, and then you just go on and multiply those sums to the power of q and p together, this entire product is going to be greater than or equal to the sum of the p plus q, or the root degree p plus q of the products of respective terms in those two sequences, and this entire sum risen to the power of q plus p. And this is actually a generalization of the Cauchy-Schwarz inequality. If you were just to plug q being equal to 1 and p being equal to 1, you will get that the product of sums of two sequences is greater than or equal to this sum of the square roots of respective terms, because this p plus q root is going to be just the square root, and this q plus p here is going to become just a 2, so we're going to be squaring this entire sum right over here. And you could actually generalize it to even more, to even a greater number of sequences. If you were to just throw in another sum right over there, there will be no problem for you. You would just first of all, consider the inequality for those two sequences, and then just multiply the resulting stuff at the other side of the inequality, but by the new sum. So I'm not gonna be proving Holder's inequality today, because it's honestly just a bunch of calculus, which is kind of beyond the scope of Olympiad. I'm probably gonna be proving this someday in the future in the Layback Math series, but not today. Today we're gonna be hopping straight into the problems. I'm gonna just be telling you guys how you use in problem solving in Olympiads, when to solve it, when to use it, and kind of how to apply it. So let's roll. Okay guys, so we are diving straight into some tough problems. We are doing the 2001 IMO problem number 1. We are given a, b, and c that are positive real numbers, and we're supposed to prove that a over the square root of a squared plus 8b c plus two similar looking fractions, but with a replaced to b and c respectively, is greater than or equal to a 1. Okay, so how are we supposed to use Holder's inequality? First of all, let's rewrite this entire sum in terms of sigma notation, and precisely speaking, in terms of cyclic sum notation that I talked about a few videos back. So you have no idea what I'm talking about right now. Just go and check it out. It's gonna look like this. It's gonna be the cyclic sum of a divided by the square root of a squared plus 8bc is supposed to be greater than or equal to a 1. Okay, so now, Holder is perfect at eliminating stuff that we don't really want, in the terms of a sum. So for example, fractions. I would love to get rid of this awfully looking denominator there. Especially given that it's, a square root inside of it, it's just awful. Yeah, so it'll be awesome to get rid of it. And actually, I could use Holder's inequality to do it. Let me just rewrite it right here. I'm gonna parenthesize this cyclic sum of a over the square root of a squared plus 8bc. Now I'm gonna just multiply it by the cyclic sum of just the square root of a squared plus 8bc. Now by Holder's inequality, maybe I will move it a little bit to the left so it doesn't really mix up with stuff on the right. It's gonna be greater than or equal to what? Our p and q are just 1. We are raising those two sequences to those two sums to a first power. And so it's gonna be something like this. It's gonna be the cyclic sum, so the index is gonna stay the same. I think it's pretty straightforward. Is going to be equal to the cyclic sum, and then the square root of the product of this stuff times this stuff. So those two this denominator here is gonna cancel out with this square root of right there, with this square root right there, not the square root of right there. And we'll get the cyclic sum of just the square root of a, and this entire thing is gonna be just risen to the power of 2. Well, that's awesome. We just got rid of this denominator. The only problem is that we've got a square root of a right there, and it's all squared. It's not quite what we really want here, but there is a nice fix for that. Let me just insert an additional a right over here. I mean, multiply this square root in the second sequence by another a. What I'm gonna get is, when I multiply through those respective terms in those sums, those a's are gonna multiply through to be an a squared. Those denominators are still gonna cancel each other out, and I'm gonna be left with just the square root of a squared, which is just, well, guess what? It's gonna be just the cyclic sum of just the a, and it's gonna be squared. I mean, precisely speaking, it should be the cyclic sum of the absolute value of a, but as a is a positive real, I don't really care about the absolute value. But, well, you see, this is a perfect situation to be in. We just got rid of all these fractions, the square roots, all that stuff. But the problem is that we had to multiply both sides of the original inequality by that second sum. So we probably did some bad stuff to the to the poor right hand side of this one, because, well, we multiplied the entire inequality, the entire original inequality, by the cyclic sum of a times the square root of a squared plus 8bc, and so the resulting inequality that we got after, maybe I will just move to the right. So the resulting inequality we got, or maybe I won't be able to, or no, I won't be able to. Shit. So I'm gonna have to move it to the left, and now I'm gonna write our original inequality. We got, well, the left hand side became the cyclic sum of just the a and then everything squared. However, the right hand side became, well, exactly the thing that we multiply the left hand side by, which is the cyclic sum of a multiplied by the square root of a squared plus 8bc. And this inequality didn't get any easier. Well, we have to find a way to multiply both sides of this inequality by some kind of a thing that does not affect the right hand side, so this one right there, so dramatically as the stuff we just came up with here. So I'm just gonna, kind of erase all that stuff, because it is just not the right solution, the right way to go, and we will think about all of this stuff once again. So there is no problem for me to just square both sides of this inequality. I mean, a, b, and c are positive reals. There's no problem for me to just square everything. I've got two positive numbers on both sides of this inequality. Squaring them will not change the sign, but squaring looks something like this. However, I can also rewrite it as taking the sum I've got on the left hand side. I mean, what I'm doing to the left hand side, I can write as taking the sum I've already got there, so the cyclic sum of a over a squared plus bc, 8bc, and multiplying it through by another sum that looks exactly like this one. And so, well, what is this thing gonna give me, you might ask? Well, it will cancel out the square root from the denominator. What I'm gonna get after applying Holder's inequality to this product over here is gonna be, I would like to use purple here. Oh yeah, I've got the color. Yeah, is gonna be the cyclic sum of the huge square root of a squared divided by a squared plus 8bc. Okay, this time it was my fault. So anyway, why is it a perfect situation to be in? I mean, we just got rid of the square root here in the denominator, and we are left with just, an a squared under a square root. Well, this is just a plain old a without any addition, multiplication, division, roots, integrals, whatever. There's no other stuff. It's just a plain old a. Well, lovely. Absolutely perfectly. The only problem is that we still have to get rid of this denominator, this a squared plus 8pc. How do we do it? Well, if we were to now take this cyclic sum we've got right there on the right hand side of the, it's to my left, so on the left hand side of this inequality, and multiply it through by a cyclic sum of just a plain old a squared plus 8bc, what we would be left with by Holder's inequality is this cyclic sum of the cube root of a squared all to the power of 3. And we're almost there. I wanted to do it. Shit. Doesn't matter. I wanted to do the Italian thing, but I had to hold my pencil, and so I could really do this thing, so I did a cross right there. Anyway, it was stupid. So, well, now the only thing we have left to do here is just multiplying this entire thing here, insert the sum by an additional a, and then the exponent here will just change and become a 3. And so this entire cyclic sum will just be the cyclic sum of just the plain old a to the power of a 3. And what is perfect about doing those operations on both sides of this inequality, rather than doing stuff that I erased earlier, so the first solution that I came up with? Well, it doesn't do any harm to the one we've got there, because the first kind of change I'm making is I'm squaring everything. So it doesn't change the right hand side at all, it just remains to be a 1. And then what I do is after squaring both sides, multiply both sides through by this guy, by the cyclic sum of a times a squared plus 8bc. But this thing is not a fraction, not a square root, it's just a cubed plus 8abc. Without a single problem there. So I can do it. I can now just kind of sum everything up. No, I can do it. I'm gonna rewrite my original problem right here. It was the cyclic sum of a all over the a squared plus 8bc, and it was supposed to be greater than or equal to 1. So now I would like to square both sides. Yeah, squaring both sides. After squaring both sides, I can apply holders to the left hand side, getting the cyclic sum of a huge square root of a all over a squared plus 8bc, and then everything is going to still be squared, and it's still greater than or equal to just 1 squared, which is just a plain old 1. And now I'm gonna just multiply both sides of this inequality through by a cyclic sum of a multiplied by a squared plus 8bc, so the exact thing I did right over there. And what I'm gonna be left with is, on the left hand side, as I showed earlier, the cyclic sum of just the plain old a all to the power of 3 greater than or equal to, and on the right hand side it's just gonna be the cyclic sum of a cubed plus 8abc. So, well, the exact same thing I got right over there, but I just kind of multiplied everything through by an a inside of the sum. Yeah, awesome, because this thing on the left hand side is nothing but just a plus b plus c to the power of 3, and on the right hand side it's just a cubed plus b cubed plus c cubed plus, and I believe it is 24abc. But guess what? It is true now. Just go on and multiply out this stuff we've got right over there, and you will get, in my opinion, it was a cubed plus b cubed plus, I mean, to the best of my memory, double a squared b plus double a squared c plus double b squared a plus double b squared c plus double c squared a plus double c squared plus 6abc, and on the right hand side it was a cubed plus b cubed plus c cubed, and then plus 24abc. Now we can just go on and cancel out the a cubed, b cubed, c cubed, and then we'll divide everything by 2, subtract those 6abc from here and from here. We're gonna get an 80abc there. And now, you know, by AMGM inequality, you can just go on and apply AMGM to those guys there, and you will get that this is perfectly greater than or equal to 18abc. But pretty nicely, well, guess what? This is exactly what we've got on the right-hand side. And so we've got our inequality proven, and I can write the beautiful square. Let's go further. Okay guys, so let's get to the problem number 2. We are once again given a, b and c to be positive reals, and we're supposed to prove the inequality that a over the square root of a plus double b plus, well, the same looking fraction but with a kind of replaced with b and c in the following ones is greater than or equal to the square root of the sum of a, b and c. How are we supposed to do it? Well, same procedure. Let's first of all rewrite this thing in terms of sigma notation, you know, just so it is nicer to look at it. So what we're gonna get is the cyclic sum of a divided by the square root of a, not a squared, but a plus double b is greater than or equal to the square root of a plus b plus a c. Lovely. So what can I do here? Well, it would be pretty nice to go on and, well, get rid of the square root on the right hand side. So maybe squaring. What will squaring do to my left hand side? Well, it would be pretty much just multiplying this sum by the same looking sum. So by whole this, I would get rid of the square root from the denominator. Well, both sides of this inequality will benefit from that, so let me go on and do it. I'm gonna go on and square both sides of this inequality up. What I'm gonna get after going on and doing this will be, I'm gonna write it, is gonna be the cycling sum of a over the square root of a plus double b multiplied by the cycling sum of a over the square root of a plus double b. I could have applied whole this directly, but who doesn't love me reading out math formulas? I think everyone loves me. I mean, at least everyone loves me reading out math formulas. It's gonna be greater than or equal to, I mean, supposedly greater than or equal to, because we still have to prove it, a plus b plus a c. Lovely. But now let's apply whole this to the left hand side. What we're gonna get is, oh wait, this a awful looking parentheses. Yeah, so CYC, the cyclic sum of an awfully big square root of a squared divided by a plus double b, everything nicely squared, is greater than or equal to, I mean, supposedly a plus b plus a c. Okay, so what do we want to do here? Well, it would be lovely to get rid of this a plus double b, this denominator from the left hand side. We hate it. We don't like fractions, you remember that for forever. Fractions bad, okay? Yeah, now what can we do in order to get rid of this denominator? We could just multiply both sides of this inequality through by, for example, a cycling sum, or maybe I will move it a little bit to the left. I can never, get enough space when I'm writing something to the left of a math formula. It's going to be cycling sum of a plus double a b on both hand sides. I'm gonna just copy it to the right hand side as well. Yeah, so this kind of a thing. Okay, so well, now if I do it by whole this inequality, I'm gonna change colors. I got lots of colors. I can change them. On the left hand side, I'm gonna get the cycling sum of the cube root of a squared everything cubed. Well, standard procedure, we should have put another a here in the cycling sum in order to just pump up this exponent here by a 1. So I'm just gonna do it and put in another a in both of those sums on both hand sides. I'm just gonna then get a cycling sum of plain old a to the power of 3 on the left hand side, and on the right hand side is gonna be, well, a plus b plus c, everything multiplied by the cycling sum of a squared plus double a b. Okay, but, well, what is this cycling sum? I mean, how can I rewrite this thing? Let's try and see. I mean, let's see. So what I'm gonna get here is just the plain old a plus b plus c to the power of 3. On the right hand side is gonna be a plus b plus c multiplied by, now it's gonna be a squared plus double ab plus b squared plus double bc, and then plus c squared plus double ac. But wait, this guy right there, this is just a plus b plus c all squared. So actually the left hand side is a plus b plus c all cubed, whilst the right hand side is a plus b plus c multiplied by a plus b plus c all squared. That's true. I mean, those are equal to each other, so this is definitely true. And so by this we've got our inequality proven, and I can put a lovely square here. Let's go forward. Okay guys, so let's get straight to the last problem. We have a, b and c. Once again, real numbers. The sum is equal to 3 and we're supposed to minimize the sum of reciprocals of the square roots. Lovely. So once again, first of all, cyclic sum notation. How can we write this stuff in cyclic sum notation? I mean, you know, I just kind of like doing it. It just feels more natural to use whole there when you do it. Yes, so it's gonna be the cyclic sum of 1 over the square root of a. Here is gonna be just, oh yeah, let's just write it as the cyclic sum of an a. And we're looking for some bit of a way to use those two cyclic sums and also the whole inequality to get some kind of a lower bound, a numerical lower bound on this expression right over here. So first of all, let's just, you know, try and multiply them together and use whole there, because why not? Maybe we'll, you know, get something out of it. Is going to be something like this. The cyclic sum of 1 over the square root of a multiplied by the cyclic sum of just the plain old a is going to be greater than or equal to, well, the cyclic sum of the square root of the of the a over the square root of a, which is just the fourth root of a. Shit, man, it's not quite the thing. We don't really get anything out of it because we have no idea what this thing is. But, well, if I were to now square this guy out, what I would get out of this entire inequality by using whole there would be, well, the cyclic sum of the product of 1 over the square root of a times 1 over the square root of a times an a, everything under a cube root and everything cubed, but this guy over here, well, this thing is just a 1. So I would get that this entire thing would be just clearly the cyclic sum of just 1 to the power of 3, but we know what the cycle is, it's just a, b, and c. And so this thing would be just 1 plus 1 plus 1, which is 3, and all to the power of 3. But now, what is the cyclic sum of a? Well, that's a plus b plus c, but this thing was told to be 3, or said to be 3. And so we get that 3 multiplied by the square of the sum we're trying to estimate a lower bound on is greater than or equal to 3 to the power of 3. And so, taking the square root and dividing by 3, or maybe the other way around, dividing by 3 and then taking the square root, we will get that our cyclic sum of 1 over the square root of a is going to be greater than or equal to a 3, and well, this is the minimized expression. Okay, so I hope you guys enjoyed this video. Well, if you did, then like and subscribe to my channel not to miss out on any future content I'm gonna be posting, and well, hopefully see you next one. Bye.